An ice cube tray of negligible mass contains 0.350 kilograms of water at 18.0 degrees Celsius. How much energy must be removed to cool the water to minus 10 degrees Celsius? Okay, so what we have here is a tray full of water that we are going to use to freeze into ice cubes. So I'll illustrate this in two parts. I'll illustrate this as water, which is part of our system. I'll signify that with m sub w for the mass of the water. We know the mass of the water is 0.350 kilograms. The other thing in our system is the ice cube tray. I'll signify that with just an m sub t for tray, but they say the mass of the tray is negligible. So what that's going to mean for our purposes is that we don't have to consider the heat exchange between the water and the ice cube tray. Now, we know the water is initially at a temperature of 18 degrees Celsius, which I'll signify as T18. At some point, we may want to convert to Kelvin temperature, but let's reserve that until later, because remember, a change in Celsius temperature is equal to the change in Kelvin temperature. So at the end, we may not need to convert into Kelvin if we have our temperatures expressed in terms of differences. Now, we want to end up with the water cooling to minus 10 degrees Celsius. So I'll just signify that as T minus 10 as a reminder of what it is, and this is going to be minus 10 degrees Celsius. And as a matter of fact, that might be a bit to write T minus 10 every single time. So I'm going to go ahead and relabel the initial and final temperatures. Let's just call the initial temperature T1, and let's call the final temperature T2. And that'll be a little bit easier notationally. Now, let's illustrate this process. So again, because the mass of the ice cube tray is negligible, we don't really have to consider thermal energy changes of it. But we do have to for the water. So let's illustrate this process for the water conceptually. So we have water that we want to eventually freeze into ice. And I'll just signify that m sub I for the mass of the ice. And we know that the mass of the water and the mass of the ice is going to be the same. In order to transform from water into ice, the water is going to have to lose some energy. So we will consider this amount of energy that needs to be lost. I'll just call that Q for the energy to be lost with the environment. To go from liquid water to solid water, there's going to be a phase change. And finally, to continue to cool until we get to our final temperature, the ice is going to have to continue to lose thermal energy. So now that I'm illustrating heat lost by the water and heat lost by the ice, I'm going to notate those with different subscripts. The heat lost by the water, I'll call that Q sub W. The heat lost by the ice, I'll call that Q sub I. And then there's going to be a phase change here. So the phase change, in order for the phase change to occur, there is also going to be energy that has to be transformed. or energy that has to go into breaking and rearranging and reforming molecular bonds. So I will call that Q sub P for the phase change. Let's illustrate this process with a temperature energy diagram. I find these useful to help me conceptualize various problems. So the vertical axis will correspond to temperature. That temperature axis can either be in Kelvin or it could be in Celsius, as long as you're consistent. For this problem, I am going to choose to at least conceptualize it in terms of Kelvin. And remember, Kelvin and Celsius are related by the relationship that a Kelvin temperature is equal to a Celsius temperature plus 273.15 Kelvin. So a temperature on the Kelvin scale is just shifted upward from the Celsius scale. The horizontal axis will correspond to energy, and we could express our energy in terms of, I guess, kilojoules if we want, since our specific heats are in terms of kilojoules. Okay, now let's illustrate this process. So I'm going to assume that the mass of the water has a certain amount of initial energy, which I'll start off with this on the right side of the graph. Since we're going to be losing energy, we'll be going from right to left as our temperature changes. So we will just call this first state of energy E1, and this first state of energy takes place at temperature T1. So what's going to happen is our water is going to cool until it gets to 0 degrees Celsius, which also happens to be 273.15 Kelvin. I'm going to signify that with just a T0 to remind myself that's the freezing point of water. So again, the temperature will decrease as we lose energy until we get the freezing point, at which time a phase change is going to occur. And then after the phase change occurs, and actually let's go ahead and label that. So we'll just call this phase change. In this range, we were still water. And then after the phase change occurs, our now newly formed ice will continue to cool until we are at minus 18 degrees Celsius. So I will label that temperature T2. That's an energy I'll call E2. So let's look at the regions in which these different processes are occurring. So the region from right to left, we're in water. Then we are phase changing from water to ice, and then we have transition to ice. In the region in which we're water, we have to lose a certain amount of energy, which we will call QW. Then when we are phase changing, we're going to have to lose more energy, which we'll call QP. And when the ice finally cools to its final temperature, we will say a certain amount of energy is going to be lost, which we'll call QI. So to calculate the total energy that has to be lost, in other words, the change of energy for our ice, for our water transitioning to ice, that is going to be QW for the water, plus QP for the phase change, plus the heat lost as the ice cools to its final temperature. Now remember, for solids and liquids, heat exchanged is given by Q equals the mass of the solid or liquid times the specific heat capacity times the change of temperature. Now, This occurs while there are temperature changes, not when there is a phase change. So when the water is first cooling down from its initial temperature, we would have the mass of the water times the specific heat of water times the final temperature until we reach the phase change, which I'm calling T0, minus the initial temperature, which I will call T1. So again, that is in the range in which we are cooling down from our initial temperature of 18 degrees Celsius. Then our water undergoes a phase change as it transitions from liquid water to ice. So the heat loss during that phase change is actually going to be given by minus the mass of the water times the latent heat of fusion for the water. Now we should remark that the latent heat of fusion for the water is 334 kilojoules per kilogram. We should also note that the specific heat of water in its liquid form is 4.19 kilojoules per kilogram. And while we're at it, we should note that the specific heat for ice is 2.10 kilojoules per kilogram. So we know those three quantities. We could continue with our problem, recognizing that after the phase change is complete, our liquid water will have been transformed into solid ice. So we have the heat exchanged as the solid ice continues to cool to minus 10 degrees Celsius is equal to the mass of the ice, the specific heat of the ice, times the final temperature of the ice, which we call T2, minus the initial temperature of the ice, which is at the freezing point of water. We now have all the information we need to find the change of energy as our water cools down to ice. So it is, again, the heat exchange in the water phase, plus the heat exchange during the phase transition, plus the heat exchange during the ice phase. This is mass of the water, specific heat of the water, times the temperature change of the water, minus the mass of the water, latent heat of fusion of the water, plus mass of the ice, specific heat of the ice, times the temperature change of the ice. At this point, let's recognize that the mass of ice is the same as the mass of water. This allows us to factor out the mass of the water from our expression, leaving us with the mass of the water times the specific heat of water times the temperature change while we're in the water phase minus the latent heat of fusion of water plus the specific heat of ice times the change of temperature while we are in the ice phase. Now we've carried this as far as we can go algebraically, so it's time to plug in numbers. Before we plug in numbers, I realized that I forgot to write down the correct unit for the specific heat of water and ice. The correct unit for the specific heat of water is the kilojoules per kilogram Kelvin. And the correct unit for the specific heat of ice is also the kilojoule per kilogram Kelvin. It's important to get those units right so we could do a unit check as we plug in numbers to help verify the validity of our answer. Now let's finally plug in numbers. So the mass of the water is 0.350 kilograms. The specific heat of water is 4.19 kilojoules per kilogram Kelvin. times the temperature change of water, which is 0 degrees Celsius minus 18 degrees Celsius, minus the heat of fusion of water, which is 334 kilojoules per kilogram, plus the specific heat of ice, which is 2.10 kilojoules per kilogram Kelvin, times the temperature change while we're in the ice phase, which is minus 10 degrees Celsius minus 0 degrees Celsius. Now we should recognize that the temperature changes here, or we have temperature changes. So even though we have Celsius degrees here, and even though in the units for specific heat we have the Kelvin in the denominator, remember, changes in a Celsius temperature is equal to the same changes in Kelvin temperature. So I don't really have to convert numerically any numbers. I could keep these as changes and recognize that since I have a change of Celsius degree, those units are going to cancel with our Kelvin in the denominator. So that'll make life a little simpler for ourselves. Continuing our unit check, we should cancel out the kilograms in numerator and denominator, since a kilogram is in every term. And that leaves us with the final units of kilojoules, which we would expect kilojoules to be the units for this problem. So that now we've simplified the units and verified that the units are going to be in kilojoules, let's plug these numbers into our calculator. So after plugging these numbers into my calculator, I get that the amount of energy lost is 151 kilojoules. So we did it. We figured out how much energy needs to be lost to transition from liquid water at 18 degrees Celsius to ice at minus 10 degrees Celsius.